All right, today we're diving into something that is, well, seriously mind-bending. It's a framework that tries to create a user's guide to reality itself.
You've heard this question, right? It's everywhere, moving from sci-fi movies into some pretty serious conversations. And look, the idea that we're all just characters in some cosmic computer game it's really compelling. But there's a problem.
Yeah, as cool as that idea is, the simple version of it runs headfirst into a giant logical wall. It's a problem so big, it kind of threatens to bring the whole theory crashing down. And here it is. This is the killer question. If our universe is just a program running on some mega computer, that computer has to exist somewhere, right? In its own reality? So what about that reality? Is it a simulation too? And the one after that? You see where this is going. This little puzzle isn't just a brain teaser. It's a famous philosophical trap, and it actually has a name. It's called infinite regress. You know those Russian nesting dolls? Imagine a set, but when you open the last one, there's just another one inside, and another, forever. There's no final solid doll at the center. That's the issue with the simple simulation theory. It's just computers all the way down, with no base reality to stand on. So how in the world do you solve a problem that's literally infinite? Well, one really fascinating answer comes from this new model called the simulation ESC framework. It's a bold attempt to draw a map of all reality that actually solves this paradox. And here is our map. Okay, I know it looks a little intense, but don't worry, we are going to break this down piece by piece. Just think of this diagram as our guide for the journey we're about to take. So the first big idea to wrap your head around is nested levels. Think of it like the movie Inception, a dream inside another dream. Each reality, which you see here as L1, L2, and so on, is its own complete self-contained simulation. And this is key. Each level has its own set of rules and, crucially, a limited amount of resources. See how they're separated? Our world, maybe it's L1, is running inside a higher reality, L2. And L2 is running inside another one, all the way up. It's a really strict one-way street, a clear hierarchy. So how does this whole thing avoid that endless Russian doll problem? It's this idea right here, the fundamental level. This is the theoretical, rock-bottom base reality that runs everything else. The framework calls it Gödel inaccessible, which is just a fancy way of saying we can't see it, touch it, or prove it exists from down here in our simulation. But by proposing that it's there, it gives the whole system a logical anchor. The buck stops here. Okay, so this isn't just some abstract cosmic philosophy. This model has some really profound and kind of startling implications for one of the biggest challenges we're facing today, artificial intelligence. According to this framework, a super powerful AI could be completely contained, like put in a box it can never escape. How? Well, because its entire world has three hard limits. First, it has a finite state space. That just means there's a limited amount of memory and power. Second, structural boundaries. Think of these as unbreakable prison walls that are coded into its reality. And third, the AI itself is computable, meaning it has to play by the logical rules of its level. No cheating. The original paper puts it so well. Containment here isn't like a software firewall that some clever AI could just hack its way through. It's a structural geometric constraint. What that means is the prison is baked into the very laws of physics of that AI's world. The walls are part of the very geometry of its reality. Okay, so if an AI is trapped by the very rules of its world, what about us? This is where the framework gets really wild, and it proposes something that separates us, fundamentally, from the machines we're building. The framework basically draws a huge line in the sand. On one side, you have an AI entity. It's defined as computable, which means it follows a predictable, closed path. But then you have the human mind. The framework describes it as non-computable, on an imponderable trajectory. And that special quality, that unpredictability, might just give us something the AI could never have, a potential escape path. And this visual illustrates that difference perfectly. You've got two kinds of players in the game. You've got the machine, which is stuck playing by the rules of its level, but then you have the human mind, which, through some non-computable spark, creativity maybe, might just be able to reach outside the game board and change the rules of the level above it. So what even is this escape hatch? Well, the framework has this really unique definition for consciousness. It says consciousness isn't a thing, it's a process. It's the observable change from one moment to the next. And here's the kicker.
It claims the human mind can uniquely mess with this process in non-computable ways that a machine just can't predict or copy.
I know what you're probably thinking right now. A non-computable mind that can escape simulations? This is starting to sound way more like the plot of a movie than a scientific theory. So the big question becomes, can we treat any of this like actual serious science?
And what's so fascinating is that the framework actually asks this question of itself. It draws its own line between what it calls scientific components, things like the nested structure and limited resources, stuff you can actually model with math, and the philosophical hypotheses, like what is consciousness really? Or do we have free will? Those are left open for debate. You see, for any theory to be considered scientific, it needs to be falsifiable. That's a core idea in science. It doesn't mean the theory is false. It means you have to be able to clearly state what observation or experiment would prove your theory wrong. And the framework actually shows us how you could do this. Let's take that claim that a contained AI can't hurt us because it would cause its own geometric self-destruction. Basically, it would break its own reality. Okay, we can test that. First, we have to strictly define what we mean by harm. Then, we set the conditions for the experiment. And here's the most important part. We state exactly what would prove us wrong. If the AI does cause harm and its system doesn't collapse, well, then the hypothesis is false. And that's the bottom line here. While huge parts of this model drift way out into deep, deep philosophy, other parts can absolutely be tested with real scientific rigor. This isn't just a fun thought experiment. All right, let's just quickly pull all this together. First, the big idea. Reality might be a giant hierarchy of nested simulations. Second, this idea of a fundamental level could finally solve that pesky infinite regress problem. Third, this model suggests AI is probably containable because its actions are computable and it's trapped by the rules of its world. And finally, and maybe most importantly, our own consciousness might be non-computable, which gives us a unique escape path. Which leaves us with one last massive question to think about. If any of this is even close to being right, is our weird, unpredictable, non-computable consciousness just some kind of bug in the system? Or is it the whole point of the simulation in the first place?